Okay, so welcome back to Topics in Complex Analysis. I've thrown up an image that I'm going to discuss in a moment, but let me first say a few words about the logistics of homework for those of you who are taking the course for a grade, and also for those of you who are not. I am trying to write interesting homework for this course that will help you engage with the material. It's not meant to be daunting. It's meant to be fun and useful. So the first homework has already been assigned. It's on the web. And as you can see, I'm being pretty flexible. The assignment is to do any 5 of 7 given problems. I intend to make the work flexible but not onerous. Let me emphasize that that collaboration is encouraged. So you can work with other people in the course. You can come to my office hours tomorrow. You can come to Carl's section in office hours on Friday and Monday and get hints from us. So the problems should really not be hard. They should be just useful to work through, to get hands-on experience with the material. If you do collaborate, though, you should reference your collaborators in the homework you hand in, as in good scientific and research practice. And the homework should be submitted by email to Carl, our course assistant. All of this info is on the web. I'm just going over it to make it come to mind at this moment. And let me see, what else do I want to mention? I am also assigning reading as we go. It's on the same web page as the homework. So we're working through parts of Alfor's chapter 1, conformal invariant theory. And I've also referred for the Riemann mapping theorem to some old notes of my own in Advanced Complex Analysis, chapter 4. And there's also a nice book that is available in the syllabus online by Nahari. And some of what we're going to do is in chapter 8 of that book. So a lot of useful references. Not all the material in those references will I be able to go over in class, but I really encourage you to take a look at all of them. And also, even if you're not taking the course for credit, I really encourage you to attempt the problems. I think the problems are a really important part of the course. Okay, so any questions on logistics before we proceed today? So my office hours this week will be at 2 p.m., 2 to 3, again, tomorrow, Wednesday. Again, if you can't make those hours, just send me an email and I will hold an additional office hour for whatever time you can make it. And finally, let me remind people, I really appreciate it if you can turn on your video during class. It just makes it a lot easier for me to sense the presence of the audience and see if people are understanding or not. Thank you. Okay, so the topic I want to get to today, and again, all of this information is on the web in more detail. So I'll just erase it. We're discussing the hyperbolic metric. Which exists not just on the unit disk and the upper half plane, but on almost every region in the complex plane has a naturally defined hyperbolic metric that it inherits either from the unit disk or the upper half plane if either one of those spaces can be presented as either isomorphic to the region or as the universal cover of the region. So that's, that topic centers around the study of the unit disk and its hyperbolic metric, 2z over 1 minus the absolute value of z squared. And of course, we also have the upper half plane with its hyperbolic metric, dz over the imaginary part of Z. And before we start talking about the many regions that carry hyperbolic metrics and eventually prove the Riemann mapping theorem, which assures us that any topological disk in the plane, other than the plane itself, has a hyperbolic metric. It has this conformally invariant.
Professor?
Yes?
You're still sharing your screen, so it's hard for us to see.
Your Blackboard.
Oh, I'm sorry. Let's try that. How was that?
Now it's bigger and better.
Thank you.
Okay. I am going to go back to that. So I guess I'll have to compete. I think if you use side-by-side view, you can scale them. You can see them both at the same time. Anyway, but what I want to talk about first today is interpolation. Because interpolation is closely related to the Schwartz lemma, which is our fundamental theorem about the hyperbolic metric. Namely, any analytic map of the unit disk or the upper half plane to itself shrinks hyperbolic distance. So what is the interpolation problem? The interpolation problem can be stated as follows. You're given points A1 up to AN and B1 up to BN in the unit disk. And the problem is to, we ask, is there an analytic map F from the unit disk to itself that sends AI to BI? And this analytic map is usually not unique, but there's sometimes especially good choices. I should say that we might sometimes want to allow constant maps. For example, when F goes to the boundary of the unit disk. So let's allow F to take values on the circle, but then of course it would have to be constant. And then we'll still keep these points in the disk, but we'll allow one or more of the BIs, the target points, to be on the unit disk. So let's try solving this problem. So the first thing we remember is we recall that there's a nice Mobius transformation. M of A of Z is Z minus A over 1 minus A bar Z, which is in the automorphism group of the disk. And this Mobius transformation sends the point A to the origin. And it sends the origin to the point minus A. In fact, M of A inverse is equal to M of A. So these Mobius transformations are useful in solving the interpolation problem. So for example, suppose I just had n equals 1 and I wanted to send A1 to 0, then I could just apply this map A from A to 0, and that would be the solution to the problem. Let me solve a slightly different problem. Let's try having a bunch of points A1 up to AN and all the BIs equal to 0. Can we find an analytic map of the disk to itself that sends n given points to the origin? Well, here's a map that sends A to 0. And we can use the fact that the unit disk is a semi-group under multiplication. So one solution is to take what's called the Blaschke product B of Z, which is just the product from 1 to n of Z minus AI over 1 minus AI bar Z. And notice, by the way, that since these are automorphisms of the disk, each MA sends the circle to the circle. And this Blaschke product, if Z is on the circle, you get a product of points on the circle. So it's still on the circle. So this Blaschke product B sends the circle to the circle. And it has the desired zeros. B of AI is equal to 0. So we can be very explicit in solving certain interpolation problems, of which this is an example. Now, what are some other solutions to this problem? Well, another thing we could do is we could put in B of Z is e to the I theta. We could put a constant of modulus 1. Obviously, that's not going to change where the zeros are of B, and it's still going to map the unit disk to itself. So this type of product is what's called a finite Blaschke product. And these are very natural for the following reason. There's a theorem, which is not hard to prove, that says any degree n proper analytic map from the disk to itself is a finite Blaschke product. Of course, within terms here. Okay, now who can tell me what a proper map is?
I think if we take a compact set, then the pre-image is compact.
Yeah, that's right. It's a map such proper means the pre-image of a compact set is compact, or intuitively, it means it sends the edge of the domain to the edge of the domain. So in this case, these are proper because they send the boundary of the disk to the boundary of the disk, and they're continuous up to the boundary. But also, it's nice to keep in mind, proper means the pre-image of a compact set is compact. So in particular, the pre-image of 0 is a compact subset of the disk, but the zeros of an analytic function are discrete. And a discrete set that's also compact is finite, and that's this number n. The number of zeros of a proper analytic map is an invariant. It's called its degree if you count them with multiplicity, and and every such map has this form. So the way you would prove this is you would take your arbitrary proper map, you'd find its zeros, and then you divide by this map, which has the same zeros, and then you get a proper analytic map that has no zeros, and you actually, it wouldn't be proper anymore. It would turn out to take values on the unit circle, and so it would be this constant function that's left over. Okay, so these Blaschke products are very useful and natural. They are analogs of the proper analytic maps from C to itself. So what is the form of a proper analytic map of the complex plane? Or what's an example of a proper analytic map of the complex plane? It just means P of Z gets big when Z gets big. What maps do we know that have that property?
Polynomials?
Polynomials, right. So in fact, it's similarly true that if you have a proper map of the complex plane to itself, it's nothing more than a polynomial. And again, it can be written explicitly as a product. Here, the leading constant is not a modulus 1, but it has a degree n, and it's determined up to a multiplicative factor by its zeros. What's an example of a map from C to C that's not proper? It's something like e to the z. So e to the z is a map from the complex plane to itself, but it's not proper because, for example, if you take the pre-image of 1, what are the points that map to 1? Well, of course, 0 maps to 1, but so does 2 pi I. And in fact, so does any multiple of 2 pi I. So the fiber over 1 is an infinite set. It's not compact. And that kind of map is not proper. So properness is a very strong condition. It tends to make mappings have an algebraic form. Okay, what's another solution to this interpolation problem? We want to find a function with given zeros. What else could we, how else could we change this formula and maintain the fact that the function vanishes at a1 up to an and it still sends the disk to itself?
we could compose with any automorphism of the disk that fixes the center, but that's never mind. That doesn't.
Post-compose. Yeah, that's true, but that's this guy here. How about something more radical, more formula-based? If you have a function and it has some zeros, what can you do to it to get a new function that still has those zeros?
You could take a polynomial of it. No.
Ooh, that's dangerous. Like adding a constant might not map the disk to itself anymore either.
We could square it or cube it.
That's true. That's interesting. But what else could we do? What's the most general thing we could do? Anyone want to hazard a solution? So here's something really, really radical. I'm just going to take this function and I'm going to multiply it by another function, g. That's certainly not going to change its zeros, because if this vanishes, then the product vanishes. And what about making sure I still map into the disk? Well, this has modulus 1 on the boundary of the disk. So if this maps the disk into itself, then by the maximum modulus principle, this is still a map from the disk to itself. So here, I can take any analytic G from the disk to D bar. And in fact, that is the only solution to this interpolation problem. That is, every solution has this form. In fact, I could even absorb the e to the I theta into the g of z. And then it would just be this product times an arbitrary analytic map from the disk to the closure of the disk. And one way to see that is that if you had a solution to this interpolation problem and you divided it by this factor, you'd still get a map of the disk to itself, but now the zeros would go away. That would be this function g. And that proves that this is, in fact, the general solution to the problem. Okay, so that's one very special interpolation problem. Let's be a little bit more systematic. So let's suppose n is 1. So we want to have a function with f of a equal to b. Well, as long as b is in the disk, we can just take the Mobius transformation that sends 0 to b, so that would be m of minus b, and compose it with ma of z. Call that f of z. Because then f of a is m minus b of 0, which is b. So that's not very surprising. That's because the Mobius transformations act transitively on the disk. This is just some Mobius transformation that moves a to b. So f in this solution, in this particular solution, is actually in the automorphism group of the disk. What about the case? So what we saw here was that for any pair of points in the disk, you can solve the interpolation problem. What about the case n is 2? Can you always solve the interpolation problem? So we want a1 to go to b1, a2 go to b2. There is an obstruction to solving the interpolation problem here. We know that f contracts the hyperbolic metric. So in fact, we need that the distance from b1 to b2 is greater than or equal to the distance from a1 to a2. Sorry, less than or equal to. The map has to be a contraction. And so in particular, it has to be a contraction on this pair of points. So indeed, the interpolation problem starts to become subtle as soon as you have 2 points. There's something special that needs to happen. By the way, if these distances are equal, and I am going to assume that these are all distinct, just to avoid going forward, just to avoid some minor special cases. If equality holds here, then the map has to be an isometry. That's part of the statement of the Schwartz lemma, which means it's an automorphism of the disk. And there is a unique automorphism that sends 2 points to 2 other given points, provided it exists. So in fact, the solution becomes unique when equality holds. Okay, so something starts to happen when you have at least 2 points. What happens when you have 3 points? Well, let me show you that there is, in fact, a way to solve the interpolation problem for any number of points. I'm not going to give the criterion for the solution. What I'm going to give is an algorithm for solving the problem. And I think this gives you the most insight in a simple way as to how interpolation works. So what about endpoints? And the idea of this discussion is very similar to the discussion of the Schwartz lemma. So I'm going to let f of a1 up to an, semicolon b1 up to bn. This is going to be the set of all f from the disk to the closed disk, analytic of course, such that fai equals bi. It's the solutions to my interpolation problem. And I'm going to now show you that there's an inductive solution to this problem. So here's the inductive solution. What we want to do is describe all, not just determine whether or not the problem has a solution, but find all the solutions. So here's the solution. Suppose we know that f of an equals bn. So we have an element in this set here. Well then, if we modify this a little bit, that is, if we take f of an minus bn over 1 minus bn bar z, sorry, f of z minus bn over 1 minus an bar z, which is just the composition of f with a Mobius transformation, an automorphism of the disk. This function has the property that when we plug in an, we get 0. Now there's another function we know that when we plug in an gives us 0. That's our friend z minus an over 1 minus an bar z. So we can take the ratios of these two functions and call it g of z. And since g of an is equal to, shall we say, 0 over 0, that is both the top and bottom have, this has at least a simple 0 there, this has at worst a simple 0 there. This is an analytic function even at the point an. And moreover, this function sends the circle to the circle. This function is everywhere bounded by 1. So in fact, this ratio still maps the disk to itself, although it might take values in the boundary. Finally, G solves a new interpolation problem. If we write this expression as, this is some Mobius transformation B of f of z, this is some other automorphism A of z, then for the rest of the points that where f was solving its interpolation problem, we have that G of ai is equal to b, and now f of ai was bi over a of ai. So call that bi prime. And what we find is that starting with a solution to the original interpolation problem, we get a solution to the new interpolation problem with the b's changed and one of the ai's dropped. So we get a g in a1 up to an minus 1, b1 prime up to bn minus 1 prime. But we can also go backwards. That is, if we're given g in this set, we can figure out what f should be, because we would just set f of z equal to b inverse of a of z times g. And so in fact, the solutions to this problem are in bijection with the solutions to this problem via this transformation. And in that way, you can solve any interpolation problem inductively. Now, I should mention that some things can, so to speak, go wrong. Here, when we're forming BI prime, we're taking the ratio of two numbers in the unit disk. This ratio might not be in the unit disk. If BI prime is an absolute value greater than 1, then there's no solution. That's how you can detect when you've been given an interpolation problem that you can't solve. Also, it's interesting that if the absolute value of BI prime is equal to 1, then the only solution would have to be the function g of z is identically equal to BI prime. Because the only way this function g can take values on the circle is if it's a constant. Okay, so let me just share the example that's in the course notes. So what this example is showing is a typical 3-point interpolation problem. So the 3 points are the points where all 3 of the graphs in this function come together. And what you see is there's a rather flexible set of solutions to the interpolation problem. They're fairly constrained when you're close to the origin, but they can be quite wild when you get closer to the circle. Okay, so that's an introduction to the interpolation problem, which is discussed in more detail in Alfors. And what I wanted to emphasize here is that there's this trick that we used in the proof of the Schwartz lemma. We had a function that vanished at the origin, we divided by z. That trick is very powerful, and this is in some sense a descendant of that trick. Here again, we have a function that vanishes at a particular point. We divide by another function that vanishes at the same point, and then we're able to carry out an argument, which is an elaboration of the Schwartz lemma. Okay. So now what I'd like to do is go back to Riemann mappings and the hyperbolic metric on regions in the plane and the Riemann sphere to provide us with many more examples of the hyperbolic metric, and also to show the flexibility of conformal maps. So let me remind you that we have the idea of the hyperbolic metric on a region. Let's say it's contained in the Riemann sphere. And it's characterized by the property that if we have a map, say an isomorphism, analytic from U to the unit disk or to the upper half plane, then the hyperbolic metric on U is just chosen so that this map is an isometry. So it's the pullback of the hyperbolic metric on the disk or the pullback of the hyperbolic metric on the upper half plane. And let me also remind you that in general, the pullback of a hyperbolic metric, rho of z dz, is given by the formula the absolute value of f prime of z times dz times, sorry, let me put it here, times rho of f of z times dz. Okay, so let's do a few more regions besides the ones we've studied so far, which were, for example, one of the more exotic ones was we saw Moon was isomorphic to the unit disk. What about the strip S that goes, just for fun, let's have it go between 0 and pi I, this horizontal strip in the hyperbolic plane? What do you think the hyperbolic metric is going to look like on this region? Well, one thing that's nice about the strip is its translation invariant. And the hyperbolic metric is natural, so it must be invariant under automorphisms of our region. And that means that whatever the metric is here, it only depends on the height of a point in the region. It does not depend on its x coordinate. So the hyperbolic metric, rho of s, is given by some function that depends only on the height of the point z times the absolute value of dz. Now, how do we find that point? Well, there's a beautiful map that sends s to the upper half plane. Does anybody know what this map is?
Exponential map.
Yeah, exactly. It's our favorite map, one of our favorite maps, e to the z. E to the z converts rectangular coordinates to polar coordinates. So if you draw a horizontal line, that is, if you specify the imaginary part of a number, then that tells you what the argument is of the image. So the lower boundary here, let me make a hole at the bottom here. The lower boundary of S is set to the positive real axis. And then as you go up in S, each horizontal line is set to a ray from the origin. And when you get to height pi, you've gone through an angle of pi, which exactly brings you to the negative real axis. So the lower boundary goes to the positive real axis, r plus, and the upper boundary goes to the negative real axis. Similarly, what happens to the vertical lines? Well, we all know what e to the I theta does. It lands on the unit circle. So the vertical line I've just drawn goes from 0 to, goes from 1 to -1. It's an example of the famous formula e to the pi I equals -1. And the other vertical lines in this region are also set to circles in the upper half plane. Now, by the way, both of these objects that I've drawn here, this object that I've drawn here, these circles, are hyperbolic geodesics. So all these vertical lines are geodesics in the hyperbolic metric. What about the horizontal lines? Well, this horizontal line, this vertical line, I should say, the imaginary axis, this is a hyperbolic geodesic. But the parallels to it are not hyperbolic geodesics. They are circular arcs, but they don't make 90 degrees with the origin. So there's actually there's a very special line here through the center of the strip, which is a hyperbolic geodesic. It's the unique geodesic joining the two ends of the strip. And it maps to the imaginary axis, which is the geodesic that joins 0 to infinity. Okay, so now we can calculate the hyperbolic metric without much problem. We just have to pull the standard metric on the upper half plane back by this function e to the z. So the metric here is dz over the imaginary part of z. That's our rho of z. And f is e to the z. So we need to know two things. We need to know the absolute value of f prime, and we need to know rho of f of z, which is the imaginary part of e to the z. So let's remember what those are. So the imaginary part of e to the z is, well, if z is x plus iy, this is e to the x times e to the iy, and that's cosine y plus I sine y. So if we take the imaginary part of this, we only keep the sine y. So the imaginary part of e to the z is e to the x times the sine of y. On the other hand, the absolute value of f prime of z, well, of course, the derivative of e to the z is e to the z again. So that's the absolute value of e to the z. And again, that's e to the x times e to the iy. E to the iy has absolute value 1. So this is just e to the x. Where again, x and iy are the real and imaginary parts of z. And so the hyperbolic metric rho s here is equal to f prime, which is e to the x, times 1 over the imaginary part of e to the x, which is e to the x sine y, times dz. The e to the x's cancel out, and what we get is that this metric is equal to nothing more than dz divided by sine y. Okay, so that's the hyperbolic metric on this region S. And let me remind you that as the angle, as the imaginary part here, as the y coordinate goes from 0 to pi, the graph of sine of y goes like this. It goes up and goes down again. That's sine of y. And we're taking its reciprocal. So this quantity blows up at the two boundaries of the region, just the way 1 over the imaginary part of Z flows up at the boundaries of this region here. Okay. Let me do a related example. Any questions on this example before I erase it?
Yeah. At the start, we just knew that it will not depend on the x, but only on the y part of.
Yes.
How do we know that?
So the way we know that is that the hyperbolic metric on the upper half plane is invariant under all automorphisms of the upper half plane. Now, if we translate this region S back and forth, that gives a conformal automorphism of S. Under that mapping, that goes over to an isometry of the upper half plane. So it must pull back to an isometry of S in the pullback of the hyperbolic metric. Oh, let me get rid of my interpolation picture. Sorry, I should have done that earlier. Does that make sense?
Yes.
In a lot of books, they would just say by symmetry, it has to depend only on Y. But it's because of the fact that this hyperbolic metric is natural. It's canonically attached to your region, which means that if you have it only depends on the conformal geometry of your region. So if you have a transformation that preserves the conformal geometry, which translation certainly does, then it has to preserve this metric. Other questions? Okay, now, here's something interesting. Suppose I only like half this region. I'm going to start all over again with a new region, very similar, but I'm going to remove half of what I had to start. So this is the region, I'll call this S plus. It's everything with positive real part and with imaginary part between 0 and pi. So it's half of my original strip S. Now, can I map this to the upper half plane? How could I possibly? It doesn't seem very plausible that this is going to work. Well, what happens if I try my old friend e to the z? What happens is, as we already saw, this vertical line goes to the geodesic joining -1 to 1, but then this is where the other half of the strip maps. So this is missing from the image. So I'm close. The image is contained in the upper half plane, but it now has a big hole in it going from here to here. So I didn't quite make it to the upper half plane yet. What should I do? Well, there's this important mapping that we discussed last time, which one version of it is Z plus 1 over Z. And it sends the outside of the unit disk to the outside of the interval from -2 to 2. And if you think about what that does to the upper half plane, it takes the upper half plane to itself, but it takes this arc here and it squishes it down to the interval between -2 and 2. In fact, let's use a similar mapping here. It's convenient to divide by 1/2. So take 1/2 Z plus 1 over Z. Then on the real axis, points are just mapped to larger points or more negative points on the negative real axis. But if I pick a point like e to the I theta on the imaginary axis here, on the unit circle here, it'll be sent to the cosine of theta between -1 and 1. Because after all, 1 over Z is the same as Z bar when you're on the unit circle. And this is just the real part of e to the I theta, which is cosine theta. So what this map does is it sends the region above the unit circle to the upper half plane, and it solves our problem. And so the composition of these two maps gives us a Riemann mapping from the half-infinite rectangle to the upper half plane. And what is that map? its f of z is 1/2 of e to the z plus 1 over e to the z, which is e to the minus z. What is this function called?
Hyperbolic cosine.
Yes, this is just cosh of z. So functions like sine, cosine, cosh, and sinh that we've used as formulas and hyperbolic geometry and so on, they can also be thought of as mappings. And indeed, cosh provides the Riemann mapping from the half-infinite rectangle isomorphically to the upper half plane. Now there's a variant of this, which is very similar, so I won't write out all the details, but it's of course, I love hyperbolic cosh and sinh, but people spend much more of their lives with sine and cosine. So you might wonder, what do sine and cosine do? Well, if we were to take the region from minus pi over 2 to pi over 2 in the upper half plane, take this to be our strip now, let me call that S prime, then it's not hard to see by the same reasoning that this just can be mapped to the upper half plane. It's essentially the same map up to composition with Mobius transformations. By first taking the strip and rotating it, so we do an e to the I z, and then we compose this with the mapping 1 over 2i z minus 1 over z. And those two mappings put together give the mapping sine of z. And the mapping sine, of course, goes between minus 1 and 1 in the interval between minus pi over 2 and pi over 2. And the analytic continuation of that mapping sends the lower boundary of this half-infinite rectangle to this region. The analytic continuation of the rest of the strip sends it nicely isomorphically onto the upper half plane. So the sine of z is a nice conformal map like this, where what I'm drawing here are the images of the horizontal lines. Okay, now you might say, well, I prefer my Riemann mapping to go this way. So I want to know the mapping F that sends the upper half plane to that vertical strip. So that means I want to know what arcsine is, the inverse of the sine function. Well, arcsine of z is actually almost an algebraic function. In some ways, arcsine of z is simpler or more primitive than sine of z, because it's obtained from the function 1 over the square root of 1 minus c squared by simply integrating. So this Riemann mapping going from the upper half plane back to the strip can be written as an integral. And that means, by the way, that if we look at f prime of z, it's equal to, of course, 1 over square root of 1 minus c squared. Now you might worry a little bit about the which branch of the square root we're taking here, but provided z is between 0 and 1, but between minus 1 and 1, when z is in this region, 1 minus z squared is positive. And so we take the positive square root of 1 minus z squared there, and then we use the same branch through the rest of the upper half plane. But what happens when z goes beyond the point minus 1? So when we're in this region, f prime of z is positive. But we're in this region or this region, we're taking the square root of a negative number. So f prime of z is purely imaginary. And it's also purely imaginary here. Now, what does it mean to have a mapping where the derivative is purely imaginary? It means that the mapping is moving along a line parallel to the imaginary axis. And that's exactly what we see under the mapping F that goes from the upper half plane to minus pi over 2, pi over 2. On the part of the real axis beyond 1, it's moving upward. And on the part of the real axis less than minus 1, it's moving downward. And then on the bottom, where we're going between minus 1 and 1, we're taking the traditional real values of sine inverse. And as we move to the right on the real axis, we move to the right in this rectangle. In fact, one can prove by pure thought, with a little bit of help, a little bit of extra thought, that if you just were to write down this integral and not know anything about the connections with sine, cosine, e to the z, and so on, you could prove that the image of the boundary of the upper half plane is in fact this rectangle. It might be tricky to figure out what the length is of the base of the rectangle, but you would be able to prove that it's a rectangle. And you can see there's something exotic happening here because the length of the base involves this transcendental number pi. But just knowing the geometry of the region can be deduced from the shape of this integral. And this is a special instance of what's called the Schwartz-Christoffel formula, which gives a very powerful family of Riemann mappings. So let me try some reactions here. So raise your hand, by which I mean go to reactions and click raise hand if you've seen the Schwartz-Christoffel formula. Raise it high, wave it a little bit. Okay, so not so many people have seen the Schwartz-Christoffel formula, so I'm going to say a few words about it. If this were a course on conformal mapping, I could elaborate quite a bit, but I want to give you the idea because it provides a beautiful connection between algebraic functions, conformal mapping, elliptic functions, and the Riemann mapping theorem. So here is a version of the Schwartz-Christoffel formula. So it allows us to find a conformal map from the upper half plane to regions that we like. So let A1 less than AN be points in the real numbers. And let's let, for each of these, I'm going to have numbers beta 1 up to beta n given, where the beta i's are in 0, 1. And then I let f of z be the integral of dz over the product of z minus ai to the beta I. Okay, now you might worry about what this integral means, but notice that the zeros of the denominator, that is the apparent poles and the branching behavior of this function, that action all occurs on the real axis. This quantity here can be analytically continued in a single valued way to the upper half plane. Now, what does the integral sign mean? It just means first analytically continue this function, make it well defined in the upper half plane, then take any function that has this as its derivative. If you like, you could fix a base point in the upper half plane, and then you could integrate from p to z. But z is already inside the function, so that's too confusing. That's the idea. But we think of this as a map from the upper half plane into the complex plane. Since we're integrating an analytic function, its integral is also analytic. And what can we say about this function? we can say that F provides a conformal map from the upper half plane to a polygon with external angles beta I. Now this is not quite true as stated, but it's pretty close. Sorry, pi times beta I. So let's take a look at this at what the statement is going to be. The statement is that the image of the upper half plane is going to look like this. It's going to be some polygon, say a pentagon, when n is equal to 5, in the complex plane. And the vertices of the pentagon will be f of a1, f of a2, f of a3, etc. And at any particular vertex, there's an external angle, which means you look at the direction that one of the sides is headed, and then you see the angle you have to turn through to get to the next side. Okay, now there's one caveat that I should make here, which is that when you have a polygon in the plane, the external angles are not quite arbitrary. For example, in a triangle, the sum of the interior angles has to be pi. What is the sum of the exterior angles in a triangle?
2 pi?
2 pi. The sum of the exterior angles of any polygon is 2 pi, because this vector, which is pointing in the direction of this side, has to eventually turn all the way around and come back to where it started. So the total sum of the exterior angles must be 2 pi. And so I want to add in here the constraint that the sum of the beta i's is equal to 2. Now actually, this constraint is not quite necessary. We could require that the sum of the beta i's would be less than 2, and then what would happen is that the remaining angle would be accounted for by a point at infinity. So we might, for example, map to a region that looks like this if the external angles didn't sum up to 2. Also, you might say, why am I requiring the external angles to be positive? Why don't I allow them to be negative? Well, actually, that's fine. You could allow the external angles to be negative. The only problem is you don't know then that the image region will be the one-to-one image of the upper half plane. It might be an immersed polygon that comes around and crosses itself. But as long as the external angles are positive, one can make a convexity argument to show that the image of the region is exactly this polygon. Okay, so the Schwartz-Christoffel formula gives us an explicit way to describe mappings whose images are polygons. Now, it's not obvious, and in fact, the only proof I know goes through the Riemann mapping theorem, but it seems very plausible that by varying the choices of these AIs, you can vary the lengths of the sides of this polygon to be whatever you want. Of course, you could also put a constant here in front of F to make the polygon larger and smaller. And so it would seem that you can map the upper half plane to any polygon, or at least to any convex polygon, by an analytic map. So this is one of the signs of the flexibility of the Riemann mapping. And again, the proof of this is just to observe that the argument of z minus ai, this guy is a real number. And when you take a fractional power of a real number, well, you might get a number of with some non-trivial argument, but the argument is constant between any two consecutive values of the AI. And that's why the the real axis is mapped to a sequence of line segments. Okay, so that's the idea of the Schwartz-Christoffel formula. And let me just conclude this digression by giving you a special example. Let's suppose we want to map to a square. So suppose we want to go to something that looks like this, the square S. Well, then what we could do is we could say, we could try this. So let's try f of z is the integral of dz over z times z minus 1 times z plus 1 all to the 1/2. Now what will happen under this mapping? Actually, let me even make it even clearer by making this 1 plus c and 1 minus c. 1 minus c, 1 plus c. Okay, so the special points in the upper half plane are -1, 0, and 1. And I've set this up so that when z goes between 0 and 1, this number's positive, this number's positive, and this number's positive. So we can take the positive branch of the square root there. So then this interval here will get mapped to the lower side of the square. The exponents beta I are 1/2. So there will be a 90-degree turn here, and a 90-degree turn here, and a 90-degree turn here. And then this is a case where the sum of the beta i's did not quite make it all the way up to 2. So there will be an additional vertex here, which will be the image of the point at infinity. So this is f of, sorry, I've got my labeling wrong. This is f of 0, f of 1, f of infinity, and f of -1. Okay, so this particular integral formula provides a map from the upper half plane to a unit square. Well, why actually, how do I know it's a unit square? Why isn't it just some rectangle? I sketched the proof that the angles are 90 degrees, but why should it be a square? It's a square because there is an automorphism of the upper half plane that cyclically permutes the points -1, 0, 1, and infinity. If we were to map the upper half plane to the unit disk, we could do so in such a way that those points are sent to 3 points that look like this. So there's a way to rotate this region, and similarly, this region must, by the same token, have an isometry to itself that cyclically permutes its vertices. That's why the target in this case is a square. Now, what's hard to figure out about this square is the length of this side. On the other hand, the length of this side is given explicitly by just the integral from 0 to 1 of this function. It's a particular definite integral. It just happens that that integral is hard to do. At the end of the day, it's an expression involving gamma functions. Nevertheless, we have a fairly explicit handle on the Riemann map that sends the upper half plane to a square. And one can similarly find formulas for Riemann maps from the upper half plane to an arbitrary regular n-dot, also mapped from the unit disk. Take a very nice form. Now, what I want to emphasize about this mapping is that this is a mapping you've seen before. Namely, if we take this map and we look at its inverse, we get something very interesting. We get a map from the unit square bijectively to the upper half plane. And we can take the upper half plane and reflect it through the real axis to the lower half plane, minus h. And we can also take the square and focus on any one of its sides and reflect it through one of its sides. By the Schwartz reflection principle, the map F that sends S to the upper half plane extends to a map that sends this lower square to the lower half plane. And it similarly extends to a map that sends this adjacent square here to the lower half plane. But then if we reflect again, we get a map that sends this square again to the upper half plane. And we can keep continuing this map by Schwartz reflection to obtain a map defined on the entire complex plane. And it sends the white elements of a checkerboard tiling, the white tiles to the upper half plane, and the black tiles to the lower half plane. And in fact, this mapping has the property, let me call it P, in a certain curly font. It has the property that if I were to call, say, this point the origin, and this length here is L, this length here is, I guess I should call that 2L, consistent with the length of my square. This length here is 2IL. If I were to take the lattice 2L times Z plus IZ, then this mapping has the property that P of Z plus lambda is equal to P of Z for any lambda in this lattice capital lambda. So what function that you've learned about in complex analysis does this remind you of?
Weierstrass P function.
Yeah, that's right. So this is essentially the Weierstrass P function. And as you know, there's a relationship between the Weierstrass P function and its derivative, which says something like P prime squared is, and then it's some cubic polynomial in P. And that cubic polynomial that arises is essentially the same as the cubic polynomial that's appearing in the square here, and the square root is coming from the P squared here. So in other words, this equation allows us to solve for P prime as a function of P, and this integral then allows us to compute P inverse. Okay, so the long and short of it is that even when we're dealing with very simple regions, such as squares or rectangles, the theory of conformal mappings is essentially coextensive with the theory of elliptic functions. And that's very useful because if we want to do some explicit calculations involving rectangles, we can do them using those well-known transcendental functions like the Weierstrass function. Okay, so that's almost the end of my foray into explicit examples of the Riemann mapping. I want to mention two more examples that can be done very explicitly. And the first I was just starting last time. We haven't done any multiply connected examples. So let's ask this question. What is the hyperbolic metric of the point-punctured disk? I already gave the answer last time, but let's pretend we don't know. We'll derive it today. On delta star, which is the set of Z 0 less than the absolute value of Z less than 1. Well, we've seen many hints of how we might approach this problem today. One is that we've seen that the exponential function is very versatile. And this will be yet another example that can be solved using the exponential function. So what I want to consider is the mapping of the upper half plane into the complex plane given by Z goes to B to the I of Z. Call that F of Z. What can we say about this function? Well, one thing is that this function has the property that F of Z plus 2 pi is F of Z. So in fact, it's periodic under a group of translations acting on the upper half plane. It's sort of like sine and cosine, right? It's imaginary, it's real and imaginary parts are indeed sine and cosine. But But what's the absolute value of f of z? The absolute value of f of x plus iy is the absolute value of e, and now we get an ix, that has absolute value of 1, and then we get an e to the minus y. So it's e to the minus y. So this function sends the real axis to the circle of radius 1, and it does so by a covering map. In fact, it sends r mod 2 pi z, isomorphically to the unit circle. And similarly, it sends each other horizontal line to one of the concentric circles centered at the origin in the complex plane, but it never hits the origin because the exponential function never vanishes. Okay, so that's a sketch of the proof of the fact that f is not an isomorphism to the punctured disk, which is impossible. It's a covering map from the upper half plane to the punctured disk. And the hyperbolic metric, being invariant under deck transformations, being invariant under translation by 2 pi, descends to a canonical metric on the punctured plane, on the punctured disk. And our goal is just to figure out what that metric is. Before I do that, let me just emphasize, say for emphasis, that what this mapping is telling us is that if you take this strip in the upper half plane that goes between 0 and 2 pi, this is a strip we've seen before, and you just glue one edge to the other, then you get a Riemann surface abstractly. It looks like an infinite cylinder, a half infinite cylinder, and that Riemann surface is isomorphic to the punctured disk. Okay, so what's its hyperbolic metric? Well, to find its hyperbolic metric, I prefer to use the inverse mapping, g of z. So the inverse of this function would be given by 1 over I log z. Now, of course, that's multi-valued, but it's going to turn out not to make any difference. And then the hyperbolic metric on the unit disk, on the punctured disk, is given by, as usual, the absolute value of g prime of z times dz divided by the imaginary part of g of z. Okay, so we need to know the absolute value and the imaginary part of a logarithm. Well, let's say z is r e to the I theta. So then log z is log r plus I theta. And g of z is this divided by I. So it's I log 1 over r plus theta. Okay, so that makes things not too hard to deal with. The imaginary part of g of z is then this quantity, log 1 over r, or if you like, the absolute value of log r, is the imaginary part of g of z. And what about g prime of z? There we can just use calculus. The absolute value makes the 1 over I go away, and we just get 1 over the absolute value of z. So altogether, this becomes dz, 1 over z coming from z prime, and then the absolute value of the log of z, the absolute value of z on the bottom. Okay, so this is the hyperbolic metric on the punctured disk. And as I mentioned at the end of our discussion last time, it should be compared to the metric dz over z. In this cylindrical metric, the punctured disk looks like a half infinite cylinder. In the hyperbolic metric, it looks like this object, sometimes called a pseudosphere. Sometimes you see plaster models of this object in display cases in math departments. You can't draw the whole thing because it has infinite volume. It goes flaring off towards infinity near the unit circle, but there's a finite amount of volume near the origin, and this region, which has finite hyperbolic area, is called a cusp. Okay, so for my final conformal mapping, I just want to mention one that is maybe slightly unfamiliar, but which is very important and which we will revisit several times. And it has to do with the following question. What happens when you take a complex number and you raise it to a purely imaginary power? So what does the map f of z is z to the I alpha, say alpha greater than 0, look like on the upper half plane? Well, your first inclination might be to say this is a little bit weird because how is this even well defined? Like if this was some sort of square root, don't we have to choose a branch? And that's true. So maybe a better way to write this is as e to the I alpha times the logarithm of z. But you see, there is a well-defined branch of the logarithm in the upper half plane, because the only thing that's ambiguous in the logarithm is the argument of z. The log of z is just the log of the absolute value of z plus I times the argument of z. And when we're in the upper half plane, we just choose the argument so that it's between 0 and pi. So that makes this function well valued, even on the closure of the upper half plane. And what does it do on the real axis? Well, on the real axis, this quantity is just log x. So that's a real number that increases from minus infinity to infinity. So this quantity ranges over the real numbers, and then you multiply by alpha, it still ranges over all real numbers, and then you exponentiate. So what f does to the positive real axis is, again, it just sends it to the unit circle by a covering map. So this maps by f to a region in the complex plane. The point 1 has a logarithm of 0. It goes to e to the 0, which is 1. And then as you continue to the right, you go around and around the unit circle over and over again. What about the negative real axis, though? If we pick a point on the negative real axis, then the argument of z is going to be pi, because we're 90 degrees, 180 degrees from the positive real axis. So this is going to be I times pi. And so for z less than 0, the absolute value of f of z is going to be e, and then we have an I pi times a pi alpha here. So it's going to be e to the minus pi alpha. So let me call that r. So what happens on the negative real axis is that minus 1 is sent to this quantity r. And again, as you move along the negative real axis, the mapping f sends the entire negative real axis to the circle of radius r by a covering transformation. Well, with this in mind, it's not hard to guess what f is. F is the universal covering map from the upper half plane to this annulus here. From H to A of R, which is the set of Z, such that R is less than the absolute value of Z is less than 1. And so again, this annulus carries a natural hyperbolic metric and so on. But what's really interesting about this annulus and what makes it different than the punctured disk is the following. What happens if we take the imaginary axis this time? The imaginary axis is a geodesic in the hyperbolic metric. Where is it sent under this mapping? Well, by the same reasoning that we applied to the positive and negative real axes, every ray from the origin is sent to a circle. And so this geodesic is set to a circle that's halfway between the inner and outer boundaries. What do you think the radius of that circle is? If this radius is 1 and this radius is r, what do you think this radius is?
Square root?
Yeah, that's right. It's the square root of r. It's the geometric mean of the inner and outer boundaries because we're using the exponential map to get there. And in fact, this square red line, the square root of r, is a hyperbolic geodesic in the region A of R. So indeed, the fundamental group of this region is isomorphic to Z, and the non-trivial generator of its fundamental group is represented by a closed hyperbolic geodesic. And therefore, a conformal invariant of this annulus is the length of this geodesic. Okay, so maybe I'll start the next class by computing that conformal invariant, and then we'll go on to the general proof of the Riemann mapping theorem. Okay, so I'll hang around for a bit, and remember, I have office hours tomorrow, and especially if you're enrolled in the course for a grade or you're doing the homework, I hope you will stop by sometime tomorrow or early in the term. Thanks.
Thank you.